this lecture, I will introduce an important concept called the reciprocal lattice. We will examine how the reciprocal lattice is related to the real lattice and what are its applications to crystallography and X-ray diffraction. So, we begin our discussion on reciprocal lattice. So, we have what we can call as the real space lattice. A real space lattice is defined by the vectors A, B and C, which are the unit cell vectors, and as we have been using them. And then I have the reciprocal lattice, which is defined by another set of 3 vectors called as the vector A star, B star and C star. And let us examine what is the relationship between these vectors A, B, C and A star, B star, C star. So, relation between A, B, C and A star, B star, C star. Well, in terms of dot products, I can write a set of relationships as follows. One set is that if I take the dot product of the reciprocal lattice vector A star and the real space vector A, this will be equal to the dot product between B star and B. It will be equal to the dot product between C star and C, and this would be equal to some positive quantity. I could call it as K square. However, in crystallography, we will put this quantity as simply unity or 1. So, we will use that the dot product between A star A, B star B and C star C would be 1. A second set of relationships is as follows. If I take the dot product between the reciprocal lattice vector A star with the real space vector B, this is going to be equal to A star C, this would be equal to B star C equal to B star A would be equal to C star dot product between C star and A star and C star and B. All of these quantities would be equal to 0. So, if I am given a set of vectors like A, B, C and the reciprocal lattice vectors A star, B star, C star, if I plug it into these relationships, then if they follow these relationships, then the 2 lattices are related in a reciprocal nature. And why we call them reciprocal is because they will have some reciprocal properties to each other. Let us examine this further, because these set of relationships allows us to look at whether the 2 lattices are related in a reciprocal way or not. However, if I am given a set of vectors, so if I am given a set of vectors A, B, C, the question is how to find the reciprocal vectors A star, B star and C star. So, let us examine this a bit. If I look at the set of relationships given in 2 above, then since the dot product, let us just take the A star reciprocal vector. So, A star dot B equals A star dot C equals 0. This implies that the vector A star is perpendicular to vector B and the vector A star is also perpendicular to the vector C, which means that the vector A star is perpendicular to the BC plane of real lattice. Similarly, B star, the reciprocal lattice B star would be perpendicular to the AC plane of the real lattice, and the reciprocal lattice vector C star would be perpendicular to the AB plane of the real lattice. Now, let us look at the reciprocal lattice vector. Let us look at reciprocal lattice vector A star and how I could find this vector given a set of vectors A, B and C. So, very clearly, since A star vector is parallel to the BC plane of the real lattice, so if I take the cross product between the vectors B and C, this will produce a vector which will be perpendicular to the BC plane, and therefore, the vector A star would be parallel to B cross C, which implies that A star vector I can write as some scalar quantity beta times B cross C. Now, let us say I multiply or I take the dot product of both on both sides by the vector A. So, I can write A star dot A equals beta times the dot product between the vector A and the vector B cross C. What should be its result? Well, we already have defined from a set of relationships 1. So, from 1 I have A star dot A equals 1. Therefore, beta times A dot B cross C must also be equal to 1. Now, what is this quantity? A dot B cross C. Let me look at this quantity through a diagram. Let me first draw the real space vectors, vector A, this is vector B, and this is vector C, completing the unit cell. So, this is the unit cell defined by the vectors A, B and C. Let me say this is O, this is A, this is B and this is C. Now, if I define the vector C in this, vector C star in this, now that vector C star should be parallel to the BC plane. So, your vector C star would be something like this. This is C star and the angle between the vector C star and C is theta. Now, let us see that if I look at this quantity B cross C, if I look at the magnitude of this is going to be BC multiplied by sine of the angle between the vectors B and C, and which is sine alpha. So, between the vectors B and C, the angle is alpha. This is nothing but the area of the parallelogram. When I take the dot product between the vector C and B cross C, then this is simply equal to the magnitude of C multiplied by the magnitude of B cross C multiplied by cosine theta. So, therefore, this simply becomes, so since the base is the area of the parallelogram, you multiply it by the vertical distance C cos theta, then this gives me the volume of the unit cell, and let me call that as V. So, therefore, A dot B cross C is nothing but the volume of the unit cell. This implies that beta equals 1 upon V. Hence, the vector A star now can be written as, the vector A star can be written as B cross C divided by the volume of the unit cell, or you can also write it as B cross C divided by A dot B cross C. In a similar way, I can write the vectors B star and C star as well. So, the vector B star would be the cross product between C and A in real space divided by the volume of the unit cell. Vector C star can be written as A cross B divided by the volume of the unit cell. One thing to note about this is that we have to be very careful in writing the cross product. We cannot, for example, cannot write A cross, instead of A cross B, I cannot write it as B cross A. We are following, so we have to follow right-handed system of axes. Otherwise, the vectors will flip. A cross B vector will point in another one direction, B cross A will point in the opposite direction. Now, let us examine a bit more what happens if I take the reciprocal of the reciprocal lattice. Taking the reciprocal of the reciprocal lattice, that is B cross B star cross C star divided by the volume of the reciprocal unit cell. So, here V star is the volume of the reciprocal unit cell. Actually, we get back the real lattice. So, this would be equal to the vector A of the real space lattice. Similarly, the real space lattice B vector would simply be the cross product between C star and A divided by V star, and then the vector C of the real lattice would be A star cross B star divided by V star. Now, how is V star related to real space lattice? Well, let us do the following exercise. What is the dot product between C and C star? The dot product between C and C star we already know is 1. It can further, now vector C, let me call it as C star C, does not matter though, C star dot C, it can be written as A cross B divided by V, this is my vector C star, and my vector, and I take the dot product with the vector C, which can be written in terms of the reciprocal lattice vector cross product, A star cross B star divided by V star. So, I can write this as A cross B dot A star cross B star divided by V star. We can now expand the numerator in the following way. I can write this as A star dot A multiplied by B dot B star minus B dot A star multiplied by A dot B star divided by V star. Very clearly, this is 0, in fact, this is also 0. So, this term is 0. These two terms, this is 1 and this is also 1, which means that this is 1 upon V star, but 1 upon V star is 1 coming from here. This implies that the volume of the reciprocal unit cell is related to the volume of the real space unit cell through a reciprocal relationship. That is, V star would be equal to the reciprocal of the volume V of the real space lattice. Now, let us take a more general reciprocal lattice vector. Just like in the real space, I can also take a vector in the reciprocal space, a reciprocal lattice vector, because the reciprocal lattice also is a lattice in a similar fashion, that it will have the translational symmetry. So, I can define a reciprocal lattice vector, I will call that as R star. In real space, I was defining it as R, and I have H A star plus K B star plus L C star, where H, K and L are integers. Now, I want to obtain some kind of a relationship for this reciprocal lattice vector R star with the real lattice. So, let me draw the following diagram to begin with. So, I have, let us say, the x is A, the x is B and the x is C, and I can define plane HKL. So, let us say this is the plane HKL, and this is A, the intercept or the plane makes with the A axis is capital A, the point at the point of intersection with the B axis is capital B, and the point of intersection with the C axis is capital C. In terms of the HKL indices, the intercept at point A would be A bar upon H. In fact, the vector, I can say OA would be A bar upon H. The vector OB would be B upon K, and the vector OC would be C upon L. So, what is the, and in fact, let me also put down, let us say that this is my vector R star. So, this is my vector R star. So, what is the relationship? So, I need to now want to find out the relation between R star and the plane HKL. So, I have R star, which is reciprocal space, and I have the plane HKL, which is the real lattice space. So, I want to find out what is the relation between R star and HKL. So, let us look at the vector R star and the vector AB, and let us take the dot product between the two. Now, vector R star, I can write it as H A star plus K B star plus L C star, and the vector AB, I can break this up into two vectors and write it as AO plus OB. Further, H A star plus K B star plus L C star dotted with, let me replace AO with, AO would be minus A by H from the figure, and the vector OB would simply be B by K. Let us take the dot product between the two. If I take the dot product between the two, you will see I can take dot product with the individual vectors in the two brackets. So, I can write this as H upon H minus H upon H A star dot A plus H upon K A star dot B plus I can write minus, take the second term in the first bracket, dot it with the first term in the second bracket, minus K by H B star dot A plus K upon K B star dot B, then third term of the first bracket L C star would be minus L upon H C star dot A, and the final term L upon K C star dot B. Very clearly, most of the terms will go to 0, because A star dot B is equal to 0, this is 0, this is 0, this is 0, and this is 0. What is left with are only two terms. This will give me minus 1 and this would give me plus 1. So, therefore, R dot AB is simply minus 1 plus 1, that goes to 0, which implies that vector R is perpendicular to the vector A. this should be R star, and here also it will be R star. So, R star is perpendicular to the vector A B. In a similar way, I can show that the vector R star would be perpendicular to the vector B C, and R star would be perpendicular to the vector A C, which implies that the reciprocal lattice vector R star H A star plus K B star L C star is perpendicular to the plane H K L. Now, what is its magnitude? I also want to find out what is the magnitude of R star. Well, let us take a unit vector n, and this unit vector n is perpendicular to the plane ABC. Then very clearly the dot product between the unit vector and the vector OA, going back to the figure again, vector OA is this. So, the dot product between the unit vector n and OA would be nothing but the interplanar spacing of the plane HKL. So, D is the interplanar spacing of the plane HKL. Now, what is the unit cell vector? Oh, what is the unit vector n? The unit vector is along the R star, reciprocal lattice vector R star is parallel to that, and therefore, the unit vector I can very easily define it as the vector R star divided by its magnitude, and I will write the magnitude without the bar, I will write it like this. So, therefore, the interplanar spacing D is the vector R star upon R star, the magnitude, dot the R star with the vector OA. Now, the vector OA is nothing but the vector A upon H. So, I write it as, so it is written as H A star plus K B star plus L C star, dot this with the vector OA, which is A by H upon the magnitude of the vector R star. Going further, the only non-zero term is H upon H A star dot A. The other terms like B star dot A and C star dot A will be 0. This divided by R star. Now, A star dot A is equal to 1, H upon H is 1, therefore, this is simply 1 upon R star, or interestingly, the magnitude of the reciprocal lattice vector R star is simply the reciprocal of the interplanar spacing D of the planes to which the R star is perpendicular. We will continue this discussion further in the next lecture. Thank you.